Hello everyone, my name is Yanni Valindras and we are the Space Monkeys. Our team is tasked with creating an artificial gravity habitat to support future crewed missions to Mars. The Habitable and Resupplyable Artificial Mars Baseline Environment, or Harambe, will be our spacecraft. Our mission was designed in such a way so that it meets the requirements and constraints provided by the Rascal NASA competition. Our primary objective is to transport a crew of 6 from cislunar space to orbit around Mars while simulating Mars's gravity. Our secondary objective is to carry a Mars lander and rover to allow for missions on the surface of Mars. Our spacecraft is designed in order to sustain 5 round trips to Mars, which will allow for an operational lifetime of 15 years. Constraints, as given by NASA, do not allow for use of nuclear power for safety reasons, no more than 750 kilowatts of solar arrays at beginning of life, and the spacecraft needs to be refueled in cislunar space.
Hi, I'm Tyler Rosenberger from the Space Monkeys. For the mission ConOps, we plan to organize our mission into several stages. First, Harambe will launch and assemble in LEO orbit, followed by a transfer to a geostationary orbit, where we'll be ready to disembark, at which point the craft will undergo a 9-month Hohmann transfer to take the craft from Earth to a Mars orbit, at which point we plan to park Harambe in a 0.5 eccentricity 5 Sol orbit around the planet. It will stay in this orbit for the entirety of its mission life, and then transfer back to Earth via another Hohmann transfer, at which point the crew can disembark. We plan to then keep the craft in this geostationary orbit until another mission is ready to launch.
With regards to mission timing, we plan to begin launching components in March of 2026, with further launches and assembly continuing through March of 2028. After getting all components in orbit, we plan to assemble the craft and move it to Geo and crew the craft in July of 2028. After refueling, Harambe will depart for Mars along a Hohmann transfer in September 2028. Transferring between the two planets takes approximately 8.5 months, meaning arrival should take place in June of 2029. Then after about 20 months of mission time in the prescribed 5 Sol orbit, we'll return via Hohmann transfer in October of 2031, where the craft remains in geoparking orbit around Earth until next mission begins.
I'm Daniel Cunningham, in charge of structures. Harambe is broken down into 2 parts. The toroid, which is comprised of the artificial gravity environment where the crew will live, and the main hull, which is comprised of storage, fuel, and the command center. The materials of Harambe are broken down into 2 parts. The shielding, modeled after ESA Structures PID-32 stuffed Whipple design, which is a 0.225 centimeter outer shell of aluminum to break up hypervelocity projectiles, 1.5 centimeters of Kevlar, 0.5 centimeters of Nextel, and then another 0.435 centimeters of aluminum for the hull of the spacecraft. The second part of the materials are the supports, which are comprised of titanium and steel. A displacement and frequency analysis were done of the system. It was found that there is a maximum displacement of 1.65 times 10 to the negative 5th meters, with the spacecraft being rigid at the tip. With the frequency analysis, the maximum displacement was found to be on the solar panel tips at a displacement of 0.00234 meters. Both of these displacements were found to be acceptable.
Hello, I'm Justin Gottheld, in charge of the launch vehicle and payload for this Harambe system. The system is going to be launched in 10 launches by the SLS Block 2B. This is the least amount of launches for any spacecraft to get it into LEO orbit. Launches will start in March of 2026, ending around March of 2028, and the crew will be launched in July. For the resupply, that will be a mix of the SLS Block 1A and the Falcon Heavy. The SLS Block 1A was chosen for its larger cargo fairing, and the Falcon Heavy for its cost efficiency when supplying the fuel. For the payload system, I was in charge of managing the overall weight of the spacecraft and choosing a lander for the crew to embark upon from the Harambe to Mars. I went with a Orion multi-purpose crew vehicle as the base, as Lockheed Martin is working on a next generation for the spacecraft. That includes thruster, fuel, and descent control.
Hi, my name is Brandon Olson, and I am in charge of propulsion and thermal control systems. For our spacecraft, we decided on a LR-91 bipropellant rocket as our main thrust rocket. We'll also use a MR-80 monopropellant thruster for orientation, and for electric, we'll use a Hall effect thruster. The propellants for the main rocket, they come out to the fuel, which is the Aerosine 50, comes out to 167 tons. For the oxidizer, which is dinitrogen tetroxide, is 311 metric tons. The tank sizes for both of these are around 5 tons, and each tank is made with aluminum that will resist the corrosive effects of the hypergolic fuels. The thermal control system for a spacecraft is modeled after the ISS. The spacecraft will operate in a range of temperatures from 21 degrees Celsius to 10 degrees Celsius. 20 degrees Celsius will be in the crew areas, and 10 degrees will be in the interior areas of the spacecraft. For thermal control, the crew compartment will be controlled by a pair of water fluid loops. Water for safety. The rest of the spacecraft will have multiple pairs of ammonia fluid loops. And where necessary, we will add heat exchangers, radiators, heaters, etc.
I am Jane Fries, and I'm in charge of the ECLSS system for Harambe. Our life support system can be broken down into 5 major categories: air revitalization, water recovery, waste management, pressure control, and fire detection and extinguishing. For air revitalization, we're using a condensing heat exchanger to extract water from the air to control humidity. For carbon dioxide removal, we'll be using a low-power carbon dioxide removal system. Then, using a saboteur reactor, we can produce up to 5 kilograms of oxygen a day. For water recovery system, we'll be using a cascade distillation system and multiple filtration ion exchanging beds to process all input water. The expected efficiency of our water processing assembly is 93%. For waste management, we'll be using a universal waste management system, which is a new waste management system under development at NASA, allowing for better efficiency. The pressure control system will work hand in hand with the air revitalization system, using a condensing heat exchanger for humidity and keeping the CO2, nitrogen, and oxygen levels at proper levels. Last but not least is fire detection and extinguishing. Harambe will be using a stable laser diode light source for fire detection. Once the fire is detected, all power and air supply will be shut down in a specific section, and then astronauts will be using a handheld CO2 extinguishers to extinguish the fire.
Hello, I'm Mustafa Wasif Alam, and I'm going to talk about the power subsystem. For this mission, we need a power system that can provide a large amount of power in a safe and reliable manner. The primary power source for Harambe was chosen to be solar cells because it is an excellent choice for this specific mission in terms of safety, reliability, and capability to produce large amount of power without adding significant amount of mass to the payload. The solar cells that will be used for this mission are the NEXT triple junction XTJ prime solar cell from Spectrolab company with beginning of life efficiency of 30.7%. This particular solar cell was chosen because it has one of the highest efficiencies in the market, and Spectrolab has a long and successful history of manufacturing solar arrays for many earlier space missions, including the ISS. The total power requirement for our spacecraft will be 250 kilowatts in Mars orbit. That amounts to a beginning of life power capability of 580 kilowatts in low Earth orbit. The area of the solar array that will be required to produce the power was calculated to be about 1400 meters squared, and the mass of the solar array would be about 1200 kilograms. Furthermore, the degradation rates for the solar arrays have been approximated to be about 0.8% per year, and that has been accounted for in our total power, mass, and area calculations. The secondary power source required for this spacecraft has to be a large-scale energy storage system with high specific energy while being reliable, safe, and durable. The primary purpose of the secondary power source will be load leveling and for providing power during eclipse periods. After performing a detailed trade study based on energy storage capabilities, mass, durability, safety, and heritage, we have chosen batteries as our secondary power source. Among the many options of batteries that are available, it was clear that lithium-ion batteries would be the best fit for our space mission because of their high specific energy and highly improved safety features. The specific batteries that will be used for our mission are the GS UASA lithium-ion batteries. We will need 72 lithium-ion batteries that will have a specific energy of 155 watt-hour per kilogram with a total mass of 254 kilogram. The total cost of the power subsystem will add up to approximately 200 million US dollars, and this was determined by analyzing the cost structure of past space missions and the International Space Station.
For the command and data handling subsystem, little's changed recently. We still plan on using BAE Systems RAD 5545 radiation hardened processor, which is a multi-core processor capable of 5.6 GIPS with a radiation hardness of 1 megarad. Furthermore, the processor is direct descendant of the RAD 750 processor, which was used for numerous Mars missions in the past, including NASA's Mars Reconnaissance Orbiter, their most recent mission to the planet. For storage, a solid-state recorder is imperative, so for safety and insurance of extra storage, the solid-state will provide 2 terabytes of storage made up of numerous small chips to prevent total memory corruption in the event of any failures or issues. To further ensure safety, we plan to back up the entire processor system with another RAD 5545 on board Harambe. Harambe's communication system will operate over the Ka band at 32 gigahertz to provide a minimum data rate of 40 kilobits per second at the maximum transmission distance when Mars and Earth are at their furthest apart. This data rate will allow for the sending of compressed videos, which will require 28 kilobits per second in addition to any return data and feedback, while providing a slight margin. To send the signal, 2 high-gain, low-gain systems will exist, composed of 5-meter dishes for directed transmission and an offset low-gain antenna for non-directional backup. These systems can be gimbaled together to minimize the possibility for component failure. To achieve data rates expected, we expect to need 10 kilowatts of power when communicating with the Deep Space Network, and will allow higher power consumptions up to possibly 50 or even 100 kilowatts to maximize data rates for maximal transmission when needed.
During the assembly period, Harambe will utilize the near-Earth network due to its heritage with previous missions and its proximity. The ground control system of Harambe will require cooperation between different locations of the DSN network, specifically Madrid in Spain, Goldstone in the United States, and Canberra in Australia. The ground control will utilize the 34-meter high-speed beam waveguides, which can ensure connectivity and are cost-effective. This will cost about $957 per hour, with a maximum delay of 21 minutes, compared to $4,770 per hour of the 70-meter antenna. Assuming continuous connection throughout the year, the maximum cost will be $25.3 million US dollars. The GNC subsystem includes position and attitude determination and delta V calculations. Harambe will be moved to cislunar space to refuel and have the crew embark. The INS system will be used to point to a designated location on Mars orbit, while stars and sun sensors will be used to determine position and attitude. GPS signals will help correct any errors. Spin stabilization will be utilized when necessary to ensure a constant spin rate. Harambe will transfer to Mars using a Hohmann transfer with eccentricity of 0.5. This will result in a periapse of 17,000 kilometers altitude, an apoapse which coincides with the aerostationary orbit. The impulsive delta V's are shown in the table below. Our design of Harambe will allow the spacecraft to complete its required 1100-day missions several times as required. To do this, we expect an upfront cost of $245 billion with additional mission cycles costing approximately $2 billion. The craft will safely provide an artificial gravity environment to its crew through the use of a rotating toroid structure surrounding its central hub. We placed high priority on heritage considerations, with preference given to components used on either the ISS or previous Mars missions. For this reason, we are extremely confident in the craft's ability to perform all of its requirements effectively.